Hello everyone, this video covers sections 5.7, 5.8 and 5.11. We're going to start with section 5.7, which is the covariance of two random variables. The definition of covariance is the following. If y1 and y2 are random variables, where each of them has expected values mu1 and mu2, then the covariance of y1 and y2 is given by the following formula. You could think of covariance as the dependence or the relationship between the two variables, y1 and y2. Okay? Now, if we were going to graph the two variables, y1 and y2, remember that we already know that each of them has a expected value or a mean. So let's say that the mean is right here for this one, and the mean here, and the mean for the second one is here. So you can think of covariance as the dependence between the two variables, or the relationship between the two variables. You will see very soon that the covariance can be positive, can be negative, or it could even be zero. Okay? If the covariance is positive, that means that as y1 increases, y2 decreases, or if one decreases, the other one decreases too. If the covariance is negative, that means that one increases, the other one decreases, so they do the opposite. If the covariance is 0, that means there is no relationship between the two, which means they are independent pretty much. Okay. Now, covariance is not the best way to measure a correlation because it depends on the units or the scale of measurement you're using for the specific problems. So instead, the best way to measure a correlation is to use a rho, which is called the correlation coefficient, which is defined to be the covariance between y1 and y2 divided by the product of their variances. And then this standardize everything, so this is a good way to measure the correlation between two variables. And the same thing is going to apply. If this is positive, well, the whole thing will be positive because these two values are positive. If this is negative, this will be negative. And remember, if this is 0, that means the correlation is 0. You will see this in a lot of detail in Math 381 in the next class. For now, you just need to be aware that the correlation has to be between -1 and 1. Now, a better formula to find the covariance will be the following theorem. This is the definition, but you will see that for computational purposes, the covariance of y1 and y2 will be equals to the expected value of y1 times y2 minus the expected value of y1 times the expected value of y2, or equals to the expected value of y1 times y2 minus mu1 times mu2. Okay? It's actually pretty easy to verify that's the case, so we can say this is the proof. If you expand this, we have the covariance of y1 and y2. It will be the expected value of y1 times y2 minus y1 mu2 minus mu1 y2, and then plus mu1 mu2. And then notice that these values are constants. So this is the same thing as expected value of y1 times y2 minus mu2, the expected value of y1 minus mu1, expected value of y2, and then mu1 mu2 because these are constants. Well, remember that this is the same thing as mu1, this is the same thing as mu2. It should be plus. So this will cancel one of this, and you will end up with just the expected value of y1 times y2 minus mu2 times mu1, or mu1 times mu2. Note from the past that if y1 and y2 are independent, then that means that the expected value of y1 times y2 is equal to the expected value of y1 times expected value of y2, which is mu1 minus mu2. So if this is the case, then the covariance between y1 and y2 will be equal to 0. All right, so recall that we have used this example like multiple times. So what will be then the covariance between y1 and y2 here? Remember, by definition, this will be the expected value of y1 times y2 minus the expected value of y1 times the expected value of y2. Recall that y1 and y2 were binomial random variables. We talked about that before. And that expected value of y1, remember, was equals to n times p, which will be 2 times 1/3, which is 2/3. And the same thing was the case for y2, was also binomial, where n equals to 2 and p is equals to 1/3, and it was also 2/3. We did this before, so you should check on this. So then we already know this part and this part. So what about this? So by definition, this will be the sum with over y1 and y2 of y1 times y2 is p of y1, y2 minus 2/3 times 2/3. This is this part. This gives you this. Now, if you multiply this by each value, like for example, if y1 is 0 and y2 is 0 times the probability is 0, obviously it will be 0. So you add all the values. You should check this part, that this will give you 2 9s. And this one obviously is 4 9s. So this is negative 2/9, which means that when one increases, the other one decreases. That should be no surprising, because remember, this was the number of contracts you can get. So if this one gets more, this one will get less, and the other way around. So if one increases, this one decreases. This one increases, this one decreases. Now let's do an example in continuous time. So we have this joint density function, which we also worked with this function before. So we want to find the covariance here. So we need to find the covariance between y1 and y2. Now, on one of the previous examples, we already find out that the expected value of y1 was equals to 2/3, and the expected value of y2 was also equals to 2/3. So we did that before. So therefore, all we need to figure out is what the expected value of y1 is y2, because we already know this will be 2/3 times 2/3. So by definition, the expected value of y1, y2 is the double integral from 0 to 1, 0 to 1 of 4y1 y2, and then you need to multiply obviously by y1 and y2, and then we're going to integrate with respect to y1 first and then y2. So this is the double integral from 0 to 1 of 4y1 squared y2 squared dy1 dy2. Now these are very, very simple integrals, so you should check this is equals to 4/9. So therefore this will be equals to 4/9 minus 4/9, which is equals to 0, which means, remember, that y1 is independent of y2, but we actually already knew that from the previous example. So therefore, we could just say automatically the covariance of y1 and y2 is 0, since we know that y1 and y2 were independent. Okay, so remember this means y1 is independent of y2. All right, let's try another example. So let's say that y1 and y2 are uncorrelated random variables, and define u1 to be y1 plus y2 and u2 to be y1 minus y2. So what will be the covariance between u1 and u2? So by the original definition, this should be the expected value of y1 plus y2 times y1 minus y2 minus the expected value of y1 plus y2 times expected value of y1 minus y2. If we distribute, this will be the expected value of y1 squared minus y1 squared, this part, and then minus the expected value of y1 plus expected value of y2 times expected value of y1 minus expected value of y2. Remember that we can just call this mu1, this is mu2, mu1, mu2. So therefore this will give you the expected value of y1 squared minus expected value of y2 squared minus, if we distribute here, this will give you mu1 squared. Then the middle terms will cancel and you end up with mu2 squared. Now recall that by definition the variance is equal to the expected value of y squared minus expected value of y squared, or you can say just expected value of y squared minus mu squared. If you solve for this one, it's the same thing as saying that expected value of y squared is equal to the variance plus mu squared. But remember, the variance is just sigma squared. So if we use that in here, we will end up with this part being sigma 1 squared plus mu 1 squared minus, this will be sigma 2 squared plus mu 2 squared, and then minus mu 1 squared plus mu 2 squared. So notice how this will cancel with that, this will cancel with that, and this just would be equals to sigma 1 squared. So sigma 1 squared minus sigma 2 squared. Okay, now let's go to section 5.8. So we're gonna do more expected value and variances. So the title of this section is expected value and variance of a linear function of random variables. So by a linear function of random variables will mean this. Let's say that u will be defined as a linear combination where a1, a2, a3 all the way to an are constants, and y1 all the way to yn obviously are random variables. All right, so let's look to the following theorem. Let's say that y1 to yn are random variables, and so are x1 to xm, where the expected value for each of these is mu I, and the expected value for each of the x's is kc j. So then we're going to define the linear combination. U1 will be a linear combination of all the y random variables, and U a linear combination of all the x random variables. So part A, which this one should be kind of obvious, the expected value of U1, well, it will be the sum of AI times the expected value of this, which will be mu I. And the variance, notice that if this is a combination, it will be the sum of a1 squared. Remember that for the variance, you have to square the value, the variance of y1. So you will have n of this, and then plus the covariance between each of them. So that's why you need the 2 of them, and then the double summation. And then if you want to find the covariance between u1 and u2, it will be defined as the double summation of the multiplications of the coefficients times the covariance between each of the y's times each of the x. All right, let's try an example with two variables. Let's say you have two variables y1 and y2, where the mean for y1 is 2, the mean for the second one is 3. This is the variance for the first one, variance for the second one, and the covariance for the two variables is equal to this. So let's say that we define u1 to be minus 2 y1 plus 4, or let's say 5 y2. So then from here, the expected value of u1 is going to be minus 2, the expected value of y1, plus 5, the expected value of y2, which in this case it will be minus 2 times 2 plus 5 times 3. So this will be minus 4 plus 15, which is 11. Now if we find the variance of u1, this will be minus 2 squared times the variance of y1 plus 5 squared times the variance of y2 plus 2 times negative 2 times 5, because remember this is a1, this is a2, times the covariance of y1 and y2. So then this will be equals to 4 times 2 plus 25 times 4, and then minus 4 times 5 is minus 20, and the covariance is 4. So this will be a plus 100 minus 80. So this is 20 minus a, which is 12. Sorry, I mean 20 plus a, which is 20a. Now, this is again an example that we have used before. Remember, this is a joint density function. We actually also have found before the expected values, and the variance for y1 was equals to 1 over 18, and the same thing for the variance of y2, it was equals to 1 over 18. So let's say that we have u to be equals to y1 plus y2, and we want to find the variance of u. So therefore the variance of u is going to be equals to the variance of y1 plus the variance of y2 plus twice the covariance between y1 and y2. But if you remember, y1 was independent of y2, so that means that the covariance between y1 and y2 was equals to 0. So therefore this disappears. So this will be just the variance of y1, which was 1 over 18. Then the variance of y2, which is also 1 over 18. So it will be 2 18ths, which is equals to 1 9. Well, let's try another example. Let's say that u is equals to just a plus b y1, and b is equals to c plus d y2. Okay? So then what will be the covariance between u and b? So again, by definition, this will be the expected value of a plus b y1 times c plus d y2 minus the expected value of u, which is a plus b y1 times the expected value of b, which is c plus d y2. Then if we distribute this, this will be the expected value. This will be ac plus adb, dy2, this and that, plus cb y1 plus BD y1 y2. Okay, so this gives you this much, then minus the expected value of A is just A because it's a constant, plus B expected value of y1, then times C plus D expected value of y2. Okay, so all of this is minus, so this bar will give you this. All right, so then if we expand this and distribute, this will be AC plus AD expected value of y2 plus CB expected value of y1 plus BD expected value of y1 y2. Okay, so again the green part is all of this, and then minus if you distribute, this will be AC plus AD expected value of y2 plus BC expected value of y1, and then finally plus BD expected value of y1 times expected value of y2. All right, so notice that this will cancel this will cancel that, this will cancel that. So the only thing left is going to be BD expected value of y1 y2 minus BD expected value of y1 times expected value of y2. So you can factor the BD, so this will be the expected value of y1 y2 minus expected value of y1 times the expected value of y2, which, you know, by definition, that's just the covariance. So therefore this will be BD times the covariance between y1 and y2. All right, so let's try another problem using the result we just got. So if the covariance between y1 and y2 divided by their standard deviation is equals to 0.2, meaning the correlation coefficient is 0.2, and then if we define u to be 1 plus 2y1 and b to be 3 plus 4y2, where y1 and y2 are this, what will be the correlation coefficient between u and b? All right, so first we need to find the covariance between u and b, and according to the result we have here, remember this is A, this is B, this is C, this is D. So this will be BD times the covariance between y1 and y2. So in our case, this will be 2 times 4 covariance of y1, y2. And then the variance of u is going to be 2 squared the variance of y1, which is 4 the variance of y1, and the variance of b, probably not the best choice for letters, but okay, the variance for b is going to be 16 the variance of y2. Okay. And I'm just going to call this sigma b squared, and this one sigma u squared. So therefore the correlation between u and b is going to be A, the covariance between y1 and y2, which we don't know what it is, which is now they have a covariance, divided by the standard deviation, which will be sigma u times sigma b, where sigma u will be 2 the square root of the variance of y1, and sigma v will be 4 the variance of y2, which technically this is just 2 sigma 1, this is 2 sigma 2. Okay, so even though we don't know the value for the covariance or this separately, we know the value of this whole part. So therefore this is the same thing as a covariance of y1 y2 divided by 2 sigma 1, and this should be 4 times 4 sigma 2. So only that this will cancel, so this will be covariance of y1 y2 divided by sigma 1 sigma 2, which we know this is equals to rho, and in this case, so the answer is the same, just 0.2. All right, so now let's go to the last section, 5.11, which is conditional expectations. And these are used a lot in higher mathematical classes, this definition. So the definition is the following. If y1 and y2 are two random variables, then the conditional expectation of y1 given that y2 is equals to 2 is given by this formula if it is continuous, and this if it is discrete, where these functions were defined before. All right, so let's do an example. So on a previous exercise, we showed that this is a valid joint density function between y1 and y2. We also found before the conditional joint density function of y1 given y2 was equals to 1 over y2, and this was true for 0 less than equals to y1 less than equals to y2. So therefore let's say we want to find expected value of y1 given the y2 is equals to y2. So therefore by definition it should be the integral of g of y1, which will be just y1, times the conditional function, which will be 1 over y2 dy1. I remember that y1 goes from 0 to y2, so therefore this is the integral of 1 over y2, because that's a constant now, from 0 to y2 or y1 dy1, which is 1 over 2 y2 y1 squared from 0 to y2, and this is technically just y2 over 2, and that's it. Now a very important result is the following, that the expected value of y1 is the same thing as the expected value of y1 given y2. This is particularly very useful when finding this directly may be tricky, so this can help you a lot, or it will make life a lot easier. Now the proof is actually not that hard. I will just go through it pretty quick. It's in the book too. So notice that by definition, this is the integral from minus infinity to infinity of y1 times the joint density function. That's the definition of expected value. This is equals to the double integral of y1 times the conditional function of y1 given y2 times the marginal function of y2. Okay, why is that the case? Well, remember that f of y1 given y2 was equals to the marginal the joint function divided by the marginal. So that's where that comes from. And then this is the same thing as the integral from minus infinity to infinity. You can separate this. This is minus infinity to infinity. And this is the definition we're just using right now for a conditional expectation times the marginal function of y2 dy2. So this equals to the integral from minus infinity to infinity. And this becomes the conditional expectation y1 given that y2 equals to y2 times the density function. Okay. So therefore this is technically the expected value, or the expected value of y1 given y2. Now there is a similar result for the variance. So the variance of y1 is the same thing as the expected value of the conditional variance plus the variance of the conditional expectation, where remember the variance of y1 given y2 is defined to be the expected value of y1 squared given y2 minus the expected value of y1 given y2, the whole thing squared. All right, so let's try one example here. Let's say that y is a binomial distribution. Obviously, you need to have n and p. The difference here is that p itself is a random variable that changes daily according to a beta distribution, alpha, beta. All right, so let me just make sure that this is clear. So y is binomial, and the parameter p, which is fixed usually, now has itself a beta distribution. So the question is, what will be the expected value of y? So the expected value of y, it can be equal to the expected value of y given p. Notice that the expected value of this is going to be np, this is binomial, but p is still random, so this will be n times the expected value of p. But p had a gamma distribution, and the expected value of a gamma distribution, remember, was alpha over alpha plus beta. So this will be n alpha over alpha plus beta. Now the variance of y is going to be a lot longer, so I'm just going to start the problem here. You should be able to complete this by yourselves. So by the definition we have on the top, this should be the expected value of the variance of y given p plus the variance of the expected value of y given p. Okay. So therefore this, by definition, remember the variance of y, since it's binomial, is np times 1 minus p. And then this will be the variance of the expected value of y given p. So it will be the variance of n times p. So the only one that is still random, remember, p is a random variable. So this will be n, the expected value of p times 1 minus p plus n squared, the variance of p. Now this one is easy to complete because you already know the variance for the gamma distribution. This will be alpha beta over alpha plus beta squared. And this is alpha plus beta plus 1. This one you have to simplify more. Remember that this will be p minus p squared. So we need to find the expected value of p, which we know what it is, minus the expected value of p squared. But remember that the variance of p is the same thing as expected value of p squared minus the expected value of p, the whole thing, in square. So therefore, if you solve for the value here, that means the expected value of p squared is equals to the variance of p plus the expected value of p squared. We have used this before, so this is not the first time we use this formula. So therefore, from here, you're going to get n times the expected value p minus n times the expected value p squared plus all of this. So this is n alpha over alpha plus beta. So this will give you this. And then minus n. So once you combine this, you will see that this will give you n alpha plus 1 divided by alpha plus beta times alpha plus beta plus 1. Okay? So again, this part comes from this when you simplify. And once you combine everything, you will end up with this beautiful thing, and alpha plus beta plus n divided by alpha plus beta squared, then alpha plus beta plus 1. And that's it.